Okay, so you have some idea what natural transformations are, right? The relationship between functors, okay? So if you look at a functor, okay, between a category and the category of sets, okay, so call that a functor, yeah? And then you have an object, and you take any object in this category, like A, okay? And then you have another functor, let's call it um, R sub A, right? Also going from category to sets. And the functors, the one that's, remember the functor we had that was just A blank from that one? So that's what I want I to be, okay? So this is one of the examples we went through, okay? And this is some general functor from categories to sets, okay? Okay. And so Yoneda's lemma says, okay, it says the natural transformations between, so the natural transformations between these two functors, okay, um, what is this? What direction is it? Let me check what direction. Let me check the direction of the statement. Hold on. I mean, the direction is obvious when you do the proof, but I want to state it here just to not confuse you too much. It goes from RA to F, yeah? So the natural transformations from these two functors, yeah, is in one-to-one correspondence, okay, with the object f of a, okay? All right. Okay, so we're a bit far off from understanding this, okay? Um, but we're not too far off from proving this.
What?
It's kind of interesting, isn't it?
Okay.
So let's let this be an exercise. I mean, you might not be able to check everything, but at least like you'll be able to come up with some things, okay? So, for example, okay, these are two sets. This is a set, yeah, yeah. So what you're saying is for every element of this set, okay, there's a natural transformation from here, yeah. So you want to define a bijection, right?
Mm.
And for every natural transformation here, okay, there's a element of that set, okay? And you can basically come up with this yourself, okay? So it's like, what it means is a bit difficult, I guess. But this is the first, like once you've done this lemma, this is like your first course in category theory, basically. Okay, so let's go one way. Let's try to go one way, okay? So imagine you have a, yeah, so we're far from understanding. I wish we had some more time to understand. Maybe if people are interested, we can go in next week, yeah? But, you know, I think this is something I can justify because I feel like this is the right way to teach people in modern society mathematics. Take into account the advances in thinking, right? Whereas the curriculum will never put this kind of stuff in. So you can see the logic, it doesn't really depend on much, does it? It's just kind of complicated, yeah? It sounds complicated. Because usually it's treated after you learn a lot of stuff, you know? So the things that go with it are a lot of sort of maybe mature observations. But this kind of stuff could also be taught at a very easy level too. you know, because we're just defining functions, you know. See, the problem is the people can't work with the abstraction because they need to know what it means, right? Whereas all we really need to know right now is that it's true. We can figure out what it means as we go, you know. Okay. So the principles in category theory, a lot of them is that you can just work naturally. There's so few things to do that the one that you do probably is the right one. There's no conflicting choices. Okay. So if you take an element of f of a, yeah. So take x in f of a, yeah. Okay. So we want to define this. Yeah. Okay. What do we have to do? Okay. So we have to define a natural transformation from R of A to F, yeah? Okay. So that means for a generic object, so an object X in the category, yeah? R of A of X, yeah?
What's R of A? Is that
it's this thing.
Oh.
Yeah, so it's a bit of a definition check. So R of A of X is just hom. So it's the functions from A to X, okay? And f of X, yeah, is just the image of that other function, yeah? So to get a natural transformation, well, one of the things you need to do is to get one of these maps that go between them, yeah? Okay. So how would you get a map? So given your X, right? How would you get a map from here to here? See? So what does that mean, right? So you got a map from A to X, yeah? That's like your F, yeah? You need to combine this data, okay, and this X to get an element of this set, yeah? Okay, so basically, let me tell you, there's not much you can do, right? First of all, there's not much you can work with. I mean, first of all, you have an A to X, yeah? One thing you can do is you can take A to X and you can go take F of that, yeah? And if you take F of that, you get a map from F of A to F of X.
Yeah.
Yeah? Okay, so that's a function between two sets. Yeah? Okay. But look, you have an element of the domain, yeah?
Yeah. Oh.
So if you have an element of the domain, you can produce an element of the codomain by just mapping it through, yeah? So what you want to do, so you just take the function and evaluate it at X, right? Okay. So the map that you get, so for this X, the natural transformation that you get, right, is defined by this function that takes, you know, F to F of X. Yeah?
And would that be F of X?
Yeah, see, this is a function from hom AX to F of X, yeah? Because this thing is in F of X. This F of X.
Yeah.
Right?
Okay.
And basically it's the only thing that could work because it's the only thing that there was in this generality. So it's going to be right, okay? but you have to maybe check it through, yeah? So, as an exercise, okay, so you have one direction, yeah? How would you define an element of f of a given a natural transformation? How would you go the other way?
You still apply f to like both sides. It's just the same thing, but like backwards.
Yeah, so so you have a natural transformation now, right? So you have a hom ax going to f of x, yeah? Such that it satisfies some things, yeah? And this is for every object x, yeah? So for every x that's an object, okay, there's a map, like this. That's what natural transformation was, if you remember. There's all these maps that relate the images of the two functors, yeah? Okay. From that, you want to define, somehow you wanted to get from this, okay? So maybe this is called, like, we can call this f of x, right? It's one for each x. So from that, you want to get to an element of, so you want to get something in f of a, right? Okay. So if you think about it, there's not really many things you can do, okay? So one thing you can do is you can specialize x to be a, yeah? Like if you think about it, right? If this proof works for any category C, right?
Yeah.
Category C might not have any objects apart from A, right? So a natural thing is to let x equal A, okay? And then what you get is you get f of A is a map from hom A to itself, yeah? To f of A, yeah? And that's nice, right? That's what you want because you have lots of things going to this now, yeah? And you want something in here, right? Yeah? That makes sense?
Yeah.
So you need something in the domain of this, and then you can get something in here, right? As the output of this function, yeah?
Yeah.
So what could you let it be? So name something you know that's in here.
Identity.
Yeah, identity, yeah?
Okay.
So now you could take this to be f of a of the identity. Yeah? So if you think about it, right, well, why is it the identity? It's the only one I could think of. It's the only one that's guaranteed to be there, yes?
Yeah.
In this generality, right? Because what A could have been anything. Some objects only have the identity in their morphisms, you know what I mean? So this kind of generality, like picking anything else would be like asserting the existence of something else, which is not true in general, yeah? That makes sense? So it feels really stupid, right? Because you're thinking of the most trivial things that come into your mind, right? Right? Which, when you're working on really specific problems, that never works, right? But in the generality, the only things that come to your mind, the only things that are there in general. So it lets you make progress. Okay? So that shows what the correspondence has to be, right? You just have to show that going one way and the other way gets you back to each other, yeah? So for example, if we took f of a of the identity, yeah? And we put it here, yeah? Or if we took this and put it into there, yeah? Would you get back? How much time do we have?
6:05.
You have to go?
Well, my parents are here.
They're here?
So I can say.
I don't know before. Oh yeah,
Mm.
is it close to being done?
Yeah. Okay, so I guess I just maybe I can use the time to summarize what we've done, yeah? So we define categories, yeah? And so in the language of categories, there are lots of interesting things that come out. So like universal properties, right? Stuff like that. For example, and the dual diagrams come out. So sometimes like you have like the disjoint union of sets and the product of sets, and you think of them as just two different constructions, yeah? But they're actually related by this nice reason, okay? And that reason comes up a lot. So in some sense, half the things you used to know before are now related to another half of things you used to know by that one reason, okay? And the idea of universal property is very interesting because it gives you an idea of like the choices that you make in maths. That's the thing you're worried about the most, right? If you're just inventing some random thing, you know, it might be not the right thing, okay? But the universal thing justifies a lot of these constructions, okay? So those are kind of just like nice features of category theory. And the main thing is it focuses on relationships, right? So it really allows you to relax what it means for two things to be the same, okay? And it gives you a notion of doing that, and it even makes those relationships concrete sometimes, and you can think about relationships between those. Okay, and then it's the first time you get some kind of weird equivalence, okay? And it turns out that's the one that actually is the most interesting. The other ones are so strict that it's not interesting. We didn't get to talk about a jointness, which is kind of sad, but one thing you could note from this, if you have time to do an exercise maybe, is that the forgetful functor and the free functor that we learned about are actually adjoint to each other. Okay? So they have this funny property that sort of, yeah, I can't go into it right now. Okay, so we didn't get to go. Representable we did get to talk about. It's when you have a functor of this form Ra for some object A. Yeah? And so I really would have liked to have some time to understand this, but maybe we can do it next time. So I guess when things are abstract, you understand them by relating them to more concrete things, yeah? So that's what a representation really is, okay? So the category of sets in this setting is meant to be the concrete set that you know about, yeah? It's as abstract as it is. Like in this level of abstractity, that's the concrete thing, okay? So studying your category is kind of like representing it by relating it from a category to this category of sets. So that's what a functor does. It relates them. Okay? Okay. But you might not know very much about those functors. Okay? But you might think you know more about these functors. Yeah? Ra. So then you want to relate the two functors together. Yeah? So you want to relate the representations that you don't understand to the representations that you do understand. Okay? And that's kind of what Yoneda's lemma is doing, right? Because the relationships between those two functors are the natural transformations, right? And it's telling you that the relationships between them are basically indexed by the elements of this set itself, okay? Oh, actually, maybe I can write down a consequence. So if you had another object B, yeah? So maybe to make this even more concrete, if you had an object B, yeah, and you considered R of B, yeah? Remember R of B is just Hom B space, yeah? And then what Yoneda's lemma was tells you about Hom, see, so what's natural transformations between R of A and R of B, yeah? Yeah? So that's just specializing F into R of B, right? Okay? And that's telling you that's equal to R of B of A, yeah? Okay, and R of B of A is by definition just Hom B to A, right? So this is the ordinary functions between, well, the morphisms between these two objects, right? Correspond one-to-one to the natural transformations between these two functions, yeah? Okay, so I guess we should at least know what has happened, sort of. We might not understand why it's happened or what it means, okay? But hopefully it piques your interest because I feel like this is definitely a choice that has been made for you basically to not teach you this instead of like functions or when you learn functions, right? It has been focused on concreteness, and it's funny like in the literature or in the lingo, people it's like when you have arguments with category theory, they just generally say by abstract nonsense, this is true. Like even mathematicians at some point thought this was too abstract. Well, not this at the moment, but like when you get further, right? It was too abstract to be practical in pure mathematics, whatever that means, right? But even the term abstract nonsense, right, is a bit prejudiced. It's almost like you're saying that it's nonsense just because it's abstract. You know what I'm saying?
Yeah.
Because what otherwise you wouldn't really put like if it was just nonsense, then it's just nonsense, right?
Yeah.
But it's almost that when you say it like that, it's like you're saying it's a nonsense because it's abstract. So in some sense, you're favoring concrete things, okay? Right? But what's concrete and what's abstract just depends on what you're focusing on. You know what I mean?
Yeah.
Like if you're studying the relationships, and those are the concrete things, and their morphisms are abstract, I guess. Okay, so this is a whole other way of looking at things, and this person called Grothendieck really made it popular. Like he proved these theorems, and like people, the way to describe it is that they look at the proof and they didn't think it was going anywhere,
Until it did.
and then by the end it was proved. So it was kind of insane, right? And so, and then the Yoneda lemma, I guess, would be sort of the first non-trivial fact, which maybe you can consider trivial because you can prove it really easily, of this theory. Okay. And if people are interested, I'll keep going because I want to understand this a bit more too. When I learned it, I never took the time to understand it. I just know how it works. You know, I never took the time to really think about it. I guess it depended on when you learned it as well. But yeah, okay.